When you look up at a clear night sky, you are not seeing the universe as it is, but as it once was. The twinkling stars above are merely ghosts of a distant past, locked in place by the ultimate speed limit of reality. Light, the absolute fastest messenger in existence, dictates a harsh truth. We are profoundly isolated in our tiny corner of the cosmos. For generations, overcoming this absolute barrier was relegated to the realm of pure fiction. We accepted that the vast silent distances between star systems were an insurmountable wall built by the laws of physics. Yet, the architecture of the universe has a strange way of hiding profound loopholes in plain sight. In the year 2024, a quiet revolution occurred within the complex mathematics of spacetime. A small research team uncovered a genuine mathematical solution, a way to move through space that does not break the speed of light, but simply does not need to. The truth is, humanity has actually found a mathematical key to the stars, even if the physical door it unlocks remains incredibly heavy. Tonight, you are going to see exactly what they discovered in those equations, and why physics just opened a door everyone thought was permanently sealed. Welcome to Bedtime Universe. As the world around you quiets down, allow the weight of the day to fade away. Join me on a slow journey through the deep emptiness of space and the elegant mysteries of theoretical physics. If you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Rest now and let us drift together into the beautiful unknown. The space that separates our sun from the rest of the galaxy is an ocean of silence so profound that it escapes human comprehension. For thousands of years, our ancestors looked up at the glittering canopy of the night sky, drawing constellations, weaving mythologies, and dreaming of touching those distant, flickering fires. Yet, the physical reality of the gulf between us and our closest stellar neighbor is a truth so chilling, it demands a quiet surrender. The nearest star beyond our own sun sits at a distance of 25 trillion miles away. That is the number 25, followed by 12 seemingly endless zeros. This is the distance to Proxima Centauri, a small red dwarf star that happens to be our closest stellar neighbor in the entire galaxy. It resides out there in the constellation Centaurus, visible from the southern hemisphere of our planet, burning quietly at a mere fraction of our own sun's brightness. It is closer to us than any other star in the vast ancient night sky. Yet, it remains separated by a chasm that defies the imagination. 25 trillion miles might not mean much intuitively, simply because our human brains did not evolve to handle numbers of that astronomical magnitude. We understand the distance to the grocery store, the distance across an ocean, but the cosmic scale requires a completely different kind of perception. Let us put this immense distance into a context that our terrestrial minds can gently grasp as we drift towards sleep. Consider the mundane velocities we experience in our daily lives on Earth. A commercial airliner soaring comfortably above the clouds cruises at about 600 miles per hour. If you were to board an airplane destined for Proxima Centauri, flying continuously through the dark without ever stopping, the journey would stretch across millions of years, outlasting the rise and fall of countless human civilizations. Even the fastest car ever built by human hands, the thrust SSC, only hit a top speed of about 760 miles per hour. If we look to the absolute extremes of our mechanical achievements on the surface of our world, a bullet fired from a high-powered rifle leaves the barrel at around 2,000 miles per hour. These speeds, while impressive to us, are less than a microscopic crawl when placed against the backdrop of the interstellar void. Now let us turn our gaze to our actual current capability to cross that terrifying distance. Let us look at one of the most distant spacecraft humanity has ever managed to build and send into the dark. That emissary is Voyager 1, launched on September 5th, 1977, from Cape Canaveral, Florida. This fragile vessel of human curiosity has been traveling through the cold vacuum of space for almost 50 years. It is currently farther from our home planet than any other human-made object in existence. In August of 2012, Voyager 1 achieved something historically monumental. It crossed the heliopause. This is the invisible, silent boundary where the sun's solar wind finally gives way to the interstellar medium. In that quiet, unseen moment, it became the first human-made object to enter the true, untamed wilderness of interstellar space. It is still out there right now, as you rest in your bed, still operational, still whispering back data across billions of miles of empty, frozen space. And it is moving fast. Voyager 1 is currently traveling at approximately 38,000 miles per hour relative to our Sun. That sounds incredibly fast, and it truly is fast by every single measure we use in our daily lives. It is moving 19 times faster than that speeding bullet fired from a high-powered rifle. In the silent dark, where there are no reference points to give a sense of motion, it is covering roughly 333 million miles every single year. That is a velocity fast enough to travel from Earth to the Moon in less than 7 hours. It is fast enough to reach the planet Mars in a mere matter of weeks during a close orbital approach. We should be profoundly proud of this machine. It is the absolute pinnacle of what our chemical propulsion can currently achieve. But then you take that magnificent, blistering velocity and you plug it into the simple equation for reaching Proxima Centauri. The math is simple, and it is entirely devastating. At 38,000 miles per hour, traveling those 25 trillion miles takes approximately 70,000 years. 70,000 years. Let that incomprehensible span of time sink into your thoughts for a moment. 70 millennia of silent drifting in the dark. To understand 70,000 years, we have to look back at our own history. 70,000 years ago, our ancestors were barely beginning to migrate out of the African continent, living in caves, surviving the brutal cold of the Ice Age, and using crude stones as tools. That is the amount of time it takes our fastest machine to reach the nearest star. When Voyager 1 finally approaches Proxima Centauri 70,000 years from now, if it were actually heading in that direction, humanity, as we know it today, will likely be entirely unrecognizable, or perhaps not even here at all. And we must remember, Proxima Centauri is merely the nearest star. It is the absolute closest stepping stone in a galaxy containing hundreds of billions of stars. If you wanted to visit Sirius, the brightest star that graces our night sky, the journey would take about 150,000 years at Voyager's current speed. Sirius sits 8.6 light-years away. And what about Betelgeuse, the massive red supergiant marking the shoulder of the constellation Orion. It is about 550 light-years distant. A Voyager-class probe heading toward that brilliant red beacon would not even arrive before our own sun exhausted its hydrogen fuel, began swelling into a red giant, and consumed the inner planets, including the very Earth from which the probe was launched. The engineering reality of this situation is brutal. You cannot inch your way to the stars by building slightly faster chemical rockets. The cruelty of this distance is not just physical, it is an existential boundary. We are trapped in a beautiful, fragile bubble, surrounded by an ocean so vast that our greatest ships might as well be perfectly motionless. The problem we face when looking out at the stars is not simply that our current engines are not powerful enough, but rather that we are fundamentally constrained by the very architecture of reality itself. To comprehend this boundary, we must consider light, the fastest entity in the known universe, which travels at roughly 186,000 miles per second, or 300,000 kilometers per second. This velocity is so extreme that at this speed, light could circle the equator of our planet more than 7 times in a single second. In the brief fraction of a moment it takes you to snap your fingers, a solitary photon could race all the way from New York to Tokyo and back again. Nothing in the natural world moves faster than this. Not physical particles, not raw energy, not even information itself can outpace it. The speed of light is the universe's ultimate speed limit, intricately built into the very fabric of reality by the unyielding laws of physics. And yet, even at that incomprehensible and blistering velocity, it takes light 4 years and 3 months just to travel from our sun to Proxima Centauri. A beam of light leaving that distant star today, right at this very instant, will not arrive at Earth until sometime in the year 2030, more than 4 years from now. This profound delay illustrates the sheer, crushing scale of the problem. This absolute barrier is not merely a technological limitation that we can eventually solve with better materials or more advanced manufacturing. In 1905, Albert Einstein published his theory of special relativity, a document that permanently altered human understanding of the cosmos. Among its many profound revelations, it mathematically proved that nothing with mass can ever be accelerated to the speed of light. The reason for this lies in a strange and unyielding relationship between velocity and substance. As any physical object approaches light speed, its effective mass increases. The closer you push a spacecraft toward that ultimate velocity, the heavier it essentially becomes, and therefore the more energy you need just to gain the next single mile per hour. By the time a ship reaches 99% of light speed, its apparent mass has already grown by a staggering factor of 7. Push it slightly further to 99.9% of light speed, and the mass increases by a factor of 22. To actually reach the exact speed of light, an object would require an infinite amount of energy. Since infinite energy does not exist anywhere in the physical universe, the conclusion is absolute. Nothing with mass can ever reach the speed of light. It is built directly into the geometry of the universe. The speed of light is more than just a measurement of velocity. It is the speed at which causality itself propagates, the absolute maximum rate at which a cause can lead to an effect from one point to another. Because we cannot violate this law, we are forced to rely on conventional propulsion, which brings us face to face with a second, equally devastating physical law. Every single rocket ever designed by human engineers works on the exact same underlying principle. The vehicle must carry fuel, it must burn that fuel, and the resulting exhaust provides the forward thrust. But fuel itself has mass, and that heavy mass must be accelerated right along with the rest of the spacecraft. This creates a vicious cycle. You need more fuel simply to push the fuel you are already carrying, which adds even more mass to the vehicle, which in turn requires even more fuel to accelerate. The mathematical relationship here is not linear. It is violently exponential. Engineers refer to this grim reality as the tyranny of the rocket equation, and it has been the absolute bane of space exploration since the very beginning of the space age. To grasp the brutality of this equation, consider the legendary Saturn V rocket, the colossal machine that carried human astronauts to the moon during the Apollo program. That magnificent feat of engineering burned through 3,000 tons of fuel in its first stage alone. That is 3 million kilograms of kerosene and liquid oxygen, entirely consumed in just 2.5 minutes of violent combustion. All of that volatile fuel, all of that immense mass, all of that staggering expense was required merely to push a tiny, fragile capsule containing 3 human beings 250,000 miles to our closest celestial neighbor. Now, attempt to scale that chemical process up to reach the stars. Proxima Centauri is 100 million times farther away than the moon. If humanity attempted to use chemical rockets to reach this neighboring star within a single human lifetime, the mathematics dictates that you would need more fuel than physically exists on our entire planet. This is not a poetic exaggeration. The actual calculations show that you would need more hydrocarbons than you could extract from every single oil deposit, every natural gas reserve, and every organic compound on Earth. And even that would not be enough. You would need to harvest the atmospheric hydrocarbons from the gas giants Jupiter and Saturn, and you would need to strip every organic molecule from every asteroid and comet floating within the solar system. Even then, the terrifying numbers simply do not work. The rocket equation does not care how much fuel you possess. It only cares about the punishing ratio between the mass of the fuel and the mass of the payload. For any interstellar travel using chemical propulsion, that ratio explodes into completely impossible values. Engineers and theoretical physicists have known about this insurmountable wall since the 1950s, which is precisely why every serious proposal for traveling between the stars has attempted to sidestep chemical engines entirely. In the 1950s and 60s, under a classified initiative known as Project Orion, researchers developed the concept of nuclear pulse propulsion. This involved the terrifying idea of detonating nuclear bombs directly behind a massive spacecraft, allowing the vessel to ride the resulting thermonuclear shockwave. Each nuclear explosion would push violently against a huge, thick steel plate connected to the ship by massive shock absorbers, violently accelerating the vehicle forward. It is a brute force, arguably insane approach to engineering, but the underlying physics actually works. Nuclear explosions release far more energy per unit of mass than any chemical reaction could ever hope to achieve. In theory, a colossal ship powered by nuclear pulse propulsion could reach a few percent of the speed of light. At just 3% of light speed, a journey to Proxima Centauri becomes a 140-year voyage instead of a 70,000-year drift. While this is still longer than a normal human lifetime, it falls within the realm of possibility for a generational ship. However, the practical problems are enormous. You would need thousands upon thousands of nuclear warheads just for one trip. The required radiation shielding would have to be incredibly massive, and the political and environmental concerns of launching such a radioactive behemoth from the surface of Earth are likely insurmountable. Other theoretical alternatives exist, but they remain equally bound by the limits of our reality. Fusion propulsion, which would burn hydrogen fuel in the same manner that stars do, fusing light elements into heavier ones to extract vast amounts of energy, would be highly efficient. Yet, we have not even mastered controlled fusion for stationary power plants here on Earth, meaning a fusion rocket capable of surviving the hostile, freezing environment of deep space is still decades away at the absolute minimum. Antimatter propulsion represents the theoretical maximum efficiency for any engine, as the collision of matter and antimatter results in complete annihilation, converting 100% of their mass into pure energy, according to Einstein's famous equation. Nothing in the universe releases more energy per unit mass. But antimatter does not exist naturally in any useful quantities. Every single atom must be meticulously manufactured in giant particle accelerators at an enormous energy cost, with current global production rates measured in mere billionths of a gram per year. Building up enough antimatter fuel for a single interstellar mission would take longer than the mission itself, and storing it safely without it touching ordinary matter and instantly exploding remains a completely unsolved engineering nightmare. Even concepts that require no onboard fuel, such as solar sails, face their own steep realities. A solar sail uses the pressure from sunlight or powerful, ground-based lasers to accelerate, utilizing the momentum carried by photons to push a reflective surface the way wind pushes a sailboat across water. The Breakthrough Starshot initiative proposed using vast ground-based laser arrays to push tiny, gram-scale spacecraft equipped with light sails to 20% of the speed of light, theoretically reaching Proxima Centauri in about 20 years to send back data. Supported by brilliant minds like Stephen Hawking before his passing, it is an ambitious project, but it simply does not scale up to accommodate crewed missions. A light sail large enough to push a spacecraft containing human beings would need to be hundreds of miles across, and the laser array required to accelerate it would demand an energy output comparable to a significant fraction of all power generation on Earth. Every single one of these exotic approaches claws just a little bit closer to practical interstellar capability, representing genuine milestones in propulsion physics. But none of them cracks the real, ultimate ceiling. The cosmic speed limit is absolute, and the energy requirements for conventional acceleration remain a heavy anchor around the neck of human ambition. We are, for all our intelligence and mechanical prowess, functionally locked inside our own solar system. Until someone asked a completely different kind of question, the stars remained forever out of reach, separated from us by an ocean of time and a strict geometry of space that simply refused to bend. The absolute boundary of light speed feels like a cage, a final sentence handed down by the unyielding laws of the cosmos. For decades, the greatest minds on Earth stared at the mathematics of general relativity and saw only a prison. But within those complex equations, hiding in plain sight, was a profound and beautiful loophole. The speed limit established by Albert Einstein is remarkably specific in its wording and its mathematical structure. It dictates that nothing can move through space-time faster than light. A rocket accelerating from a launch pad, a subatomic particle racing in a collider, a radio signal broadcast into the dark. All of these are objects or waves attempting to propagate through the fabric of the universe. For them, the speed of light is absolute and unbreakable. Einstein's equations firmly prohibit any object from exceeding that velocity. But the equations of general relativity are not just about objects moving through emptiness. They are fundamentally about the geometry of the emptiness itself. They describe how space-time is not a static, empty stage, but a dynamic, malleable fabric. Space-time can change shape. It can curve under the weight of a star, it can compress, it can stretch, and it can even expand. And crucially, hidden within the elegant math, there is absolutely no speed limit on how fast space itself can alter its own shape. This is a subtle distinction, but it is the difference between being trapped forever and finding a master key to the universe. When we say nothing can move faster than light, we must carefully define our terms. We know with absolute certainty that space itself can move and stretch faster than the speed of light, because we are watching it happen right now. When astronomers point their most powerful telescopes into the deepest, darkest regions of the night sky, they are not looking at a static painting. They are observing a universe that is relentlessly expanding. Distant galaxies are slowly receding from us, drifting away into the cosmic dark. And a curious pattern emerges when we measure their retreat. The farther away a galaxy is from Earth, the faster it is moving away from us. This recession is not a gentle drift. It accelerates the deeper you look into the abyss. If you cast your gaze out to a certain terrifying distance, roughly 14 billion light years from our home planet, you will find galaxies that are receding from us faster than light itself. This observation seems, at first glance, to be a complete contradiction of everything we just established. How can a massive galaxy, composed of billions of stars, planets, and nebulae, retreat from us at a superluminal velocity without violating the most sacred law of physics? The answer is both elegant and mind-bending. Those distant galaxies are not actually moving through space at superluminal velocities. They are not firing massive cosmic engines to break the light barrier. Instead, the empty space between us and them is stretching. To visualize this profound concept, you must picture a vast, elastic surface. The galaxies are like tiny, fragile ants standing on a massive rubber sheet. If you take the edges of that rubber sheet and pull them outward, stretching the material, the ants will separate from one another. They are not walking away from each other. In fact, the ants could be standing perfectly still. The distance between them is growing simply because the sheet itself is getting bigger. The ants are merely riding the expansion of the fabric they stand upon. In this analogy, the ants are still bound by their own physical limitations. If an ant decides to walk across the sheet, it has a maximum speed it can never exceed. That represents the speed of light. But the rubber sheet, the fabric of reality itself, is completely unrestrained. There is absolutely no limit to how fast that sheet can stretch. In the cold, precise language of cosmology, this phenomenon is called metric expansion. It is not a fringe theory or a desperate hypothesis. It is a fundamental reality of our universe, observationally confirmed by decades of meticulous, undeniable astronomical measurements. The space between the galaxies is constantly generating more space. It is a silent, invisible tide that sweeps everything along with it. And because it is the medium itself that is stretching, it carries the celestial bodies apart without any of them ever needing to accelerate through the void. They feel no crushing gravitational forces, no violent G-forces from acceleration, because locally, in their own little pocket of the universe, they are practically sitting still. The galaxies remain at rest while the universe rearranges the distances around them. This revelation completely shifts the paradigm of interstellar travel. For nearly a century, our brightest engineers have focused entirely on building faster ships, trying desperately to push metal and fuel through the unyielding resistance of spacetime. We were like sailors trying to row a tiny wooden boat against a hurricane. But the observation of metric expansion proved that the ocean of space is not a passive fluid. It is an active participant in the motion of the cosmos. If nature can stretch the fabric of reality to carry entire galaxies across the void at speeds that mock the light barrier, it forces a revolutionary thought. The ultimate barrier is not a wall to be broken. It is a wave to be ridden. This stretching of the void happens in utter silence. There is no engine noise, no explosive exhaust, just the quiet, relentless growth of the distance between all things. It is a mechanism of the universe so vast and so deeply embedded in the structure of reality that it completely bypasses the restrictions of mass and kinetic energy. When a galaxy is carried away by metric expansion at a speed faster than light, its internal physics remain perfectly undisturbed. The stars within it continue to burn, the planets continue to orbit, and any light emitted within that galaxy still travels at the exact speed of light relative to its immediate surroundings. The laws of physics are preserved flawlessly, even as the galaxy as a whole crosses distances at impossible rates. This is the profound beauty of Einstein's geometry. It is a system of rules that is unbreakable on the local scale, yet incredibly flexible on the grandest scales. By understanding that space-time is a physical, manipulable thing rather than just an empty container, the theoretical physicists of the late 20th century realized they did not need to fight the laws of nature. They just needed to learn how to speak the language of the void. They needed to find a way to make the emptiness work for them, to replicate the universe's own trick of metric expansion, but on a much smaller, human-engineered scale. In the year 1994, a 28-year-old theoretical physicist named Miguel Alcubierre was quietly working at the University of Wales in Cardiff. He had received his training at the National Autonomous University of Mexico and was pursuing postdoctoral work in Europe, immersing himself in the complex, mind-bending architecture of the cosmos. Alongside his rigorous academic pursuits, he was also a fan of a particular science fiction television series that had first aired in the 1960s. Star Trek was a cultural phenomenon, presenting a vision of the future where humanity explored the galaxy using a remarkable technology simply called warp drive. In the narrative of the show, characters would command their sleek starships to travel at warp 2, warp 5, or warp 9, achieving impossible velocities that allowed them to cross immense interstellar distances in mere days or hours, easily sidestepping the punishing millennia dictated by conventional physics. The television show, naturally, never offered a mathematically rigorous explanation of how this drive actually functioned. It was widely accepted as pure fantasy, a convenient narrative device designed to ferry characters between distant alien worlds. most serious physicists dismissed it entirely, secure in the knowledge that Albert Einstein's equations seemingly forbade any physical object from traveling faster than light. But Alcubierre possessed a rare and beautiful kind of curiosity. Rather than dismissing the fantasy, he decided to treat the concept of a warp drive as a formal, rigorous homework problem in theoretical physics. He sat down with Einstein's field equations, the incredibly complex mathematical foundation of general relativity that describes precisely how gravity functions by curving the invisible fabric of space-time. He approached these equations with a very specific, almost rebellious question in mind. He asked, what exact geometric shape would space-time need to assume in order for a localized region inside it to move faster than light, while ensuring that absolutely no physical object within that pocket actually exceeded the light speed limit locally? At first glance, the question sounds like a paradox, a playful attempt to cheat the unbreakable laws of nature by asking how to go faster than light without actually going faster than light. But Alcubierre had recognized the profound loophole of metric expansion. He understood that general relativity describes the shape of the universe using a mathematical concept known as a metric, which serves as a highly detailed recipe for calculating distances and the flow of time. Different metrics describe completely different shapes of reality. The metric for flat, empty space, far away from the gravitational pull of stars, is known as the Minkowski metric. The metric that describes how space-time curves around a massive, spherical object like our sun is called the Schwarzschild metric. And the swirling, twisting metric surrounding a rotating black hole is known as the Kerr metric. Every single one of these is a valid solution to the universe's ultimate rulebook. Through a mastery of tensor mathematics, Alcubierre successfully constructed an entirely new metric, a set of equations that described a highly specific bubble in the fabric of space-time. The internal architecture of this mathematical bubble is a place of profound, undisturbed peace. Inside the bubble, the metric is completely flat. Space behaves exactly as we expect it to. Time ticks at its standard, familiar rate, and any beam of light within the cabin moves at its normal, unbreakable speed. An astronaut resting inside this pocket would feel absolutely nothing unusual. There would be no crushing gravity, no violent forces pushing them into their seat, and no sensation of acceleration whatsoever. But outside the bubble, at its very boundary, the metric performs an astonishing act of geometric violence. On the leading edge of the bubble, directly in front of the spacecraft, space contracts sharply. The mathematical components shift in a way that aggressively compresses the physical distance ahead. Simultaneously, on the trailing edge of the bubble, space expands just as sharply, stretching the distances out vast and wide behind the ship. The bubble itself simply rides forward on this newly created asymmetry in the fabric of the universe. From the perspective of an outside observer watching the vessel in the cold dark, the bubble translates through the cosmos at any speed you choose to calculate, faster than light or slower than light, whatever velocity the geometry dictates. Yet, from the perspective of the fragile human inside, nothing is moving at all. The ship sits entirely at rest in a protective pocket of flat space-time that merely shifts its location because the universe immediately surrounding it is rapidly reconfiguring. The ship does not accelerate. It does not gain kinetic energy in the traditional physical sense, and it avoids all of the punishing relativistic effects of high-speed travel. It is simply surfing a wave woven into the very geometry of existence itself. When Alcubierre published his extraordinary result in May of 1994 in the prestigious journal Classical and Quantum Gravity, his 8-page paper sent quiet shockwaves through the theoretical physics community. The paper was incredibly dense, filled with complex tensor mathematics and geometric diagrams showing exactly how the metric components behaved. The excitement among his peers was palpable because the mathematics was undeniably, flawlessly correct. His metric was a completely valid solution to Einstein's field equations. It was not a clever trick, and it was not a mathematical error. He had delivered a formal proof that faster-than-light travel was not strictly forbidden by the rules of general relativity. Einstein's local speed limit held perfectly true inside the bubble and perfectly true outside of it, while the structure as a whole gracefully bypassed the cosmic speed limit. However, a deep, chilling skepticism immediately followed the initial wave of excitement. The mathematics worked flawlessly on the chalkboard, but translating that geometry into a physical reality required an ingredient that nature seemed absolutely determined to withhold from us. To bend space-time in this highly specific, asymmetric manner, to force the universe to push outward and stretch behind the ship, the warp bubble required something physicists refer to as exotic matter. Specifically, it demanded a substance possessing a negative energy density. To understand the sheer impossibility of this requirement, we must look at the natural world around us. Ordinary matter, the substance that makes up the earth, the oceans, our bodies, and the distant burning stars, possesses positive energy. A heavy rock, a drifting cloud of interstellar gas, and even the seemingly empty vacuum of space all have a positive energy density. Positive energy curves space-time inward, pulling things together, creating the attractive force we experience every single day as gravity. Negative energy would have to do the exact opposite. It would curve space-time outward, creating a repulsive anti-gravity effect that pushes matter away. Nothing in our everyday, macroscopic world behaves this way. You have never dropped a heavy object and watched it fall upward into the sky. Nor have you ever encountered a physical substance that gravitationally repels everything in its vicinity. If negative energy exists at all in the universe, it is certainly not a part of the normal material inventory we can mine or harvest. Yet, Alcubierre's beautiful warp bubble required vast, concentrated amounts of this impossible material to form the protective shell holding the flat interior space apart from the contracting and expanding boundaries. Without this vital shell of negative energy, the entire geometry would instantly collapse back into flat space. When other physicists sat down to run the grim calculations on exactly how much of this exotic matter would be needed to maintain the warp bubble, the results were completely catastrophic. Early estimates revealed that to transport a single, small starship, you would need an amount of exotic matter roughly equivalent to the mass of the entire observable universe. You would have to somehow harvest every single star, every swirling galaxy, every terrestrial planet, and every microscopic particle of dust in every direction out to the distant cosmic horizon. Convert all of that unimaginable mass into negative energy and concentrate it into a thin shell around your spacecraft. The number was so absurdly large, so profoundly disconnected from physical reality, that many brilliant researchers initially assumed they had made a simple arithmetic error in their calculations. They had not. The shape of the original Alcubierre metric was simply incredibly energy inefficient. The sharp, remarkably thin transition region of the bubble drove the energy requirements into a realm of pure impossibility. Thus, the warp drive was born as a beautiful, flawless piece of mathematical poetry, trapped behind a physical barrier so immense that for the next decade, the physics community treated it merely as an interesting intellectual curiosity, a dream permanently locked away by the sheer weight of the universe itself. For 5 long years, the warp drive existed as a beautiful ghost within the halls of theoretical physics. It was a flawless mathematical poem that ended with a punchline so cruel it seemed nature was deliberately mocking human ambition. To require the mass of the entire observable universe just to power a single, fragile starship was not a mere engineering challenge. It was a physical absurdity. It felt as though the cosmos had gracefully handed humanity a master key, only to reveal that the lock was infinitely heavier than the key holder. But theoretical physicists possess a quiet, relentless stubbornness. They are patient explorers who map the dark territories of mathematics, and when they encounter a seemingly insurmountable wall, they do not turn back. They run their hands along the cold stone, searching for the smallest, most imperceptible crack. In the final year of the 20th century, a physicist working in Belgium found exactly that kind of crack. In 1999, Chris van den Broek, a researcher at the Free University of Brussels, published a paper that completely altered the trajectory of interstellar theory. His work appeared in Classical and Quantum Gravity, the exact same esteemed scientific journal that had housed Miguel Alcubierre's original revelation just half a decade earlier. Van den Broek did not attempt to find a new, miraculous source of energy, nor did he try to rewrite the fundamental laws of thermodynamics. Instead, his brilliant insight was profoundly subtle, focusing entirely on the mind-bending flexibility of curved space-time itself. To understand his breakthrough as you drift towards sleep, we must first gently unravel how our human minds perceive the concepts of volume and size. In our everyday, macroscopic world on the surface of Earth, space is flat and rigidly predictable. If you build a simple wooden box that measures 1 meter wide on the outside, it will contain exactly 1 cubic meter of empty space on the inside. Our brains are hardwired by evolution to trust this unbreakable, logical relationship between the exterior physical boundary of an object and its internal geometric capacity. But in the deep, strange, and silent waters of general relativity, where immense gravity bends the very fabric of existence, this intuitive relationship completely shatters. In curved spacetime, the external surface area of a region and the internal volume it contains do not have to match each other at all. General relativity mathematically allows for incredibly bizarre and beautiful geometries, where a microscopic exterior can hide a tremendously vast interior space. The classic theoretical example of this decoupling of dimensions is a wormhole, where you could theoretically have a physical mouth the size of a standard wooden door that opens up into a vast, stretching tunnel spanning thousands of light years across the silent galaxy. The exterior and interior are decoupled by the intense curvature of reality. Van den Broek took this profound geometric decoupling and applied it directly to the architecture of the warp bubble. He looked carefully at the energy-hungry transition region, the critical boundary where space vigorously contracts in front of the ship and expands behind it, and proposed a radical, elegant redesign. He suggested shrinking the bubble's exterior boundary down to absurdly small dimensions, dropping it to the microscopic scale of 10 to the negative 15 meters. To visualize how infinitesimally tiny this is, you must look deep into the heart of a single atom. A single proton resting quietly inside an atomic nucleus is roughly 1 femtometer across. Van den Broek's proposed warp bubble would have an outer radius directly comparable to that microscopic particle. If you were standing on the outside in the cold void of space, looking for this starship with even the most advanced, highly sensitive particle detectors imaginable, the bubble would appear completely microscopic, smaller than any single atom, effectively invisible to the naked universe. But the true magic of his mathematics lay entirely on the inside. Because of the extreme, tightly wound curvature of spacetime at that tiny boundary, the interior of this microscopic speck would contain a perfectly normal-sized region of flat, undisturbed space. There would be plenty of room for a large, heavy metallic spacecraft, advanced life support equipment, and a human crew to sit comfortably, perhaps drinking coffee and watching the stars blur by in complete silence. It sounds completely impossible, akin to the fictional, magical bags found in ancient fantasy stories that are incredibly deep on the inside, yet easily carried in the palm of one hand on the outside. But in the strict, unforgiving, and rigorously tested realm of general relativity, this is not magic or fantasy. It is pure, mathematically sound geometry. The intense curvature of the space-time fabric handles the massive physical mismatch between the tiny outside universe and the cavernous interior cabin. By making this incredible geometric alteration, Van den Broek fundamentally shifted the scales of the entire interstellar problem. Because the transition region that required all the negative energy was now microscopic, the total exotic matter requirement plummeted violently. He successfully reduced the terrifying energy debt by more than 20 orders of magnitude. The impossible number dropped from something resembling the mass of the entire observable universe down to something much closer to the mass of a single gas giant planet, specifically Jupiter. Jupiter is a colossal sphere of swirling gas in our outer solar system, possessing a mass of about 2 × 10 to the 27th kilograms, which is roughly 2 trillion kilograms. It is a weight that remains entirely enormous, firmly beyond anything our current human civilization could ever hope to collect, manipulate, or artificially generate. But in the realm of theoretical physics, a reduction by a factor of 100 billion is a monumental, world-altering triumph. It meant that the seemingly impossible problem of interstellar travel had finally moved. The exotic matter requirement was no longer locked permanently to the terrifying infinite scale of the cosmos. The situation had shifted smoothly from being absolutely, fundamentally impossible to being merely ridiculously impossible. This new mathematical design also possessed an unexpected, quiet grace. It successfully satisfied certain complex quantum energy conditions, such as the weak energy condition, a mathematical criterion that rules out the most pathological kinds of negative energy, which Alcubierre's original, brutal metric had violently violated. This satisfaction was highly significant because it suggested that the microscopic design might actually be far more physically reasonable than the first iteration. However, this beautiful geometric solution came with a heavy, uncertain trade-off. By shrinking the working boundary of the warp bubble down to the microscopic scale of a single proton, the design required the curvature of spacetime to remain perfectly smooth and well-behaved at atomic length scales. And this is a realm where human knowledge currently fades into shadow and speculation. At the incredibly small scale of an atomic nucleus, the smooth, predictable rules of Einstein's general relativity give way to the chaotic, bubbling uncertainty of quantum mechanics, where quantum effects completely dominate. Nobody on Earth knows for absolute certain whether the fabric of space-time behaves classically at those subatomic depths, simply because the physics community has never been able to run an experiment to test it. We do not have the instruments, and nobody currently knows how to even perform such a delicate experiment. Yet, despite this lingering, profound mystery, Van den Broek's work injected a deep sense of hope back into the darkness. He proved that the energy requirements for bending the universe were not fixed absolute laws bound to the size of the cosmos, but variables that could be manipulated and sometimes dramatically shifted with clever, elegant geometric choices. The door to the stars was still incredibly heavy, requiring the mass of a planetary giant to pry it open. But the hinges had been oiled, and the brilliant minds of the world began to realize that, perhaps, with enough time and enough mathematics, other optimizations might be entirely possible. The evolution of human understanding rarely occurs in a single, blinding flash of insight, but rather through a slow, meticulous chipping away at the seemingly impossible. By the early 2000s, the theoretical landscape of interstellar mechanics had begun to mature, shifting from a collection of mathematical curiosities into a quiet but profoundly active area of research where specialized physicists shaved tiny fractions off the energy budget with each passing year. Yet, the numbers were still anchored to celestial scales, requiring the mass of entire planets to fuel a single journey. The engineering picture remained shrouded in the thick fog of theoretical abstraction, until a physicist working for the most prestigious space agency on Earth walked into the conversation and completely reshaped the architecture of the dream. In the year 2011, the center of gravity for this pursuit briefly shifted to Houston, Texas, specifically to the sprawling complex of NASA's Johnson Space Center. This facility is globally recognized for its mission control and its history of guiding massive, chemical-burning rockets into the void. But hidden within its bureaucratic structure was an internal research division known as Eagleworks, the Advanced Propulsion Physics Laboratory. Eagleworks was a sanctuary for speculative physics, a quiet place where brilliant engineers were granted the rare freedom to explore concepts that sounded indistinguishable from science fiction, yet possessed deep, undeniable roots in actual mathematics. It was here that they studied wormholes and exotic propulsion schemes, treating them not as fantasy, but as extreme engineering problems that might one day, in some incredibly distant future, become relevant to actual mission design. It was within this unique environment that a physicist named Harold White had been meticulously studying Miguel Alcubierre's original work for years. White understood the dense mathematics on a profound level, and he was acutely aware that the energy requirements for bending reality were completely absurd. However, His deep immersion in the equations allowed him to see something that others had overlooked. He recognized that the terrifying energy demands depended heavily on the specific geometric shape of the warp bubble itself. He suspected that there was vast room for optimization hiding in the curvature, subtle alterations that previous researchers had simply missed in their broader calculations. In September of 2011, at a gathering called the 100-Year Starship Symposium held in Orlando, Florida, White presented a geometric redesign that shocked the specialists in attendance. This symposium was a rare convergence of academic physicists from major universities, NASA engineers, representatives from private space companies, and futurists, all united by a shared interest in the incredibly long-term future of space exploration. White did not stand before them to debate whether the warp drive was theoretically valid. He took the underlying mathematics of general relativity as a given. What he presented was a pure, masterful exercise in engineering optimization. The critical change he introduced involved a fundamental rethinking of the thickness of the bubble wall. In Alcubierre's original concept, and in almost all the variations that followed it, the transition region, the specific area where normal space sharply shifted into contracted or expanded space, was incredibly thin. The metric changed with violent sharpness over a very small distance, creating a steep, brutal gradient in the geometry of the universe. White demonstrated that this extreme sharpness was exactly what drove the energy costs into the realm of the impossible. To solve this, he proposed widening the transition zone, softening the blow against the fabric of reality. Instead of a razor-thin shell of bending space, his bubble featured a thick, gradual, and incredibly gentle boundary. The compressed region holding the ship forward and the expanded region pushing from behind would still perform their necessary work, but the change would occur over a much larger physical volume, creating a softer, less extreme gradient. Furthermore, he radically altered the overall cross-sectional shape of the bubble. Instead of a perfect sphere, White calculated that the bubble should be shaped like a torus, a geometric form resembling a standard donut. The spacecraft would sit safely in the quiet, flat space occupying the hole in the middle. This specific torus geometry elegantly concentrated the severe space-time warping only in the most necessary regions, leaving other areas relatively undisturbed, which dramatically reduced the integrated energy cost across the entire mathematical structure. When White finally ran the complex numbers using this thicker wall and this torus geometry, the results were staggering. The requirement for exotic matter dropped from the mass of the planet Jupiter down to approximately 700 kilograms. 700 kilograms is roughly 1,500 pounds, which is the equivalent mass of a large, heavy motorcycle. The sheer scale of this reduction is difficult to truly grasp. Compared to the mass of the entire observable universe, or even the mass of a massive gas giant, 700 kilograms is almost mathematically trivial. If this impossible, negative energy substance could somehow be manufactured and gathered in a pure, concentrated form, 700 kilograms of it would comfortably fit inside a single, medium-sized room on Earth. Of course, the proposition was still impossible, primarily because human civilization had never produced even a single microscopic fraction of a gram of this exotic matter. But it was now an impossibility existing on a completely different scale. The problem had evolved, It had shifted from demanding an impossible amount of an impossible substance to requiring a merely incredibly difficult amount of an impossible substance. White's ambition did not stop at mathematical optimization on a chalkboard. He proposed that Eagleworks could actually attempt to physically test whether incredibly small, microscopic amounts of space-time warping could be artificially generated in a laboratory setting. To achieve this, his team constructed a highly delicate optical device known as a White-Jude warp field interferometer. The underlying principle of this instrument shares a lineage with the historic Michelson-Morley interferometer, the device that helped establish the constant speed of light, and the massive instruments used decades later to detect the faint whispers of gravitational waves colliding in deep space. The setup is a beautiful exercise in precision. An interferometer works by taking a single, pure laser beam and carefully splitting it down the middle into two entirely separate paths. These twin beams of light bounce silently off perfectly aligned mirrors before eventually being guided back together to recombine. Light behaves as a wave, and if one of those two paths is altered by even the most infinitesimal fraction, if the physical distance changes by an amount far smaller than the width of a single atom, the peaks and troughs of the two light waves will no longer align perfectly when they meet. They will interfere with each other, creating a highly distinct, measurable pattern of alternating light and dark fringes on a sensor. White's audacious idea was to set up this incredibly sensitive light trap and look for micro-scale space-time warping around a specifically designed piece of hardware. The apparatus consisted of high-voltage capacitor rings meticulously arranged in a very specific geometry at the heart of one of the laser paths. The hypothesis was that if the warp field theory was indeed correct, and if the mathematics actually scaled down to microscopic sizes, the intense electric fields generated around those capacitors might just produce a tiny local curvature in the fabric of space-time itself. It would not be nearly enough curvature to physically move anything, but it could potentially be enough to stretch the space the laser was traveling through, thereby shifting the interference fringes by a measurable amount. The team at Eagleworks built the device and ran the quiet, delicate experiment in their laboratory. The results that emerged from the silence were profoundly ambiguous. White's team did report detecting some anomalous shifts in the interference pattern under certain specific conditions, a subtle trembling in the light that could be interpreted as a bending of space. But the scientific method is a rigorous, unforgiving process, and these shifts were incredibly small, barely rising above the natural background noise of the universe. There were a multitude of mundane, earthly explanations that had absolutely nothing to do with bending the fabric of reality. The incredibly slight thermal expansion of the glass optical components, tiny invisible air currents drifting through the laboratory, electromagnetic interference bleeding from the high-voltage capacitors, or even the microscopic vibrations from heavy equipment operating nearby. All of these earthly phenomena could easily produce the exact same shifting patterns in the laser light. The experimental controls in the laboratory simply were not tight enough to definitively rule out these mundane ghosts. Critics within the broader physics community rightfully pointed out a foundational pillar of scientific inquiry. Extraordinary claims require extraordinary evidence. Detecting the artificial curvature of space-time on a tabletop would be one of the most extraordinary claims in human history, and the evidence White presented simply did not meet that immense burden. It was suggestive, perhaps intriguing, but it was not definitive proof, NASA, maintaining its rigorous institutional standards, never officially claimed that warp field effects had been successfully detected, remaining careful to describe the intriguing results as strictly preliminary and requiring much deeper, further investigation. Despite the inconclusive nature of the physical experiment, the true victory of the Eagleworks endeavor was deeply cultural and profoundly significant. The mere fact that NASA, the largest and most globally respected space agency on Earth, was officially funding this research at all was a monumental shift. The agency was taking the mathematics of warp drives seriously enough to actively allocate precious resources, physically build custom hardware, and publish preliminary results for the world to see. This official involvement cast a protective layer of legitimacy over the entire field of advanced propulsion, a legitimacy it had never possessed in its 30-year history. Because of Harold White and the Quiet Laboratory in Houston, young, brilliant graduate students at universities around the globe could now safely study warp metrics and tensor calculus without their academic advisors questioning their career choices or dismissing their work as fantasy. Complex, rigorously peer-reviewed papers on warp mechanics started appearing regularly in mainstream physics journals, shedding the stigma of being relegated strictly to fringe publications. International conferences began dedicating serious academic sessions to advanced propulsion concepts. The seemingly impossible energy budget required to bend the universe had fallen from the scale of the cosmos to the mass of a planet, down to the weight of a motorcycle. The mathematical bubble had been reshaped, highly optimized, and meticulously refined through multiple iterations of human ingenuity. The fundamental agonizing problem still remained: 700 kilograms of a substance that nature refuses to provide is still an absolute barrier. But the trajectory of the science was undeniable. The dream of the stars was no longer a joke whispered in the halls of academia. It was a legitimate engineering problem, slowly yielding to the relentless patience of human calculation. The evolution of a scientific revolution often moves in unexpected directions, shifting quietly from the sprawling, heavily guarded campuses of government space agencies into the most unassuming of environments. To find the next profound leap in our understanding of interstellar mechanics, we must leave the historic launch pads of Florida and the buzzing control rooms of Texas and travel to a crowded, noisy island of glass and steel. Imagine the dense, relentless urban landscape of Midtown Manhattan, specifically an ordinary-looking office building located at 477 Madison Avenue in New York City. Surrounded by the chaotic symphony of traffic, millions of rushing pedestrians, and the endless hum of commerce, there sits an organization completely insulated from the noise of the earthly world. Inside this building, on one of the upper floors, exists the headquarters of a private research entity known as Applied Physics. This is not a sprawling university campus, nor is it a publicly funded government laboratory bound by the strict constraints of political oversight and immediate public scrutiny. It is a unique, privately funded collective of brilliant minds supported by investors who possess a deep, abiding interest in fundamental physics and the incredibly long-term future of human technology. Founded by an engineer and entrepreneur named Gianni Martire, the organization operates a highly specialized division called the Advanced Propulsion Laboratory. Their guiding philosophy is as elegantly simple as it is audaciously ambitious. They chose to stop treating the warp drive as a mere theoretical curiosity or a mathematical parlor trick, and began treating it strictly as a systematic engineering problem waiting to be solved. The team operating within these walls is deliberately small, consisting of fewer than a dozen core researchers, yet they possess a profound intellectual gravity. Armed with doctoral degrees from prestigious institutions, scientists like Alexei Bobrik, Jared Fuchs, and Christopher Helmerich spend their days mapping the abstract, invisible architecture of the cosmos. Because they are untethered from the relentless pressure of delivering immediate, profitable results, they have the absolute luxury of patience. If their meticulous calculations take an entire decade to bear fruit, that is perfectly acceptable within their walls. They are engaged in the deepest kind of basic research, peering into the fundamental geometry of the universe with timelines that outstretch standard human planning. In February of the year 2021, this quiet dedication manifested into a landmark paper published by Alexei Bobrik and Gianni Martire. The paper, titled Introducing Physical Warp Drives, appeared in the pages of Classical and Quantum Gravity, the exact same esteemed journal that had carefully housed Miguel Alcubierre's original, mind-bending proposition nearly 3 decades earlier. But what this team accomplished was fundamentally different from everything that had come before it. They did not simply offer another solitary, isolated design for a warp bubble to add to the growing pile of theoretical concepts. Instead, they stepped back and constructed a comprehensive, unifying taxonomy. They built a general framework capable of classifying every single possible warp drive, spacetime that could ever exist, essentially creating a master map or a periodic table for the geometry of faster-than-light travel. This grand classification revealed an elegant, universal truth about the nature of these theoretical machines. The researchers demonstrated that every single warp drive, without a single exception, is composed of 3 distinct geometric regions. First, there is the asymptotically flat region existing far away from the ship. This is the ordinary, familiar space that we currently inhabit, the quiet vacuum of the universe resting undisturbed, far from the gravitational influence of any massive celestial bodies. Second, there is the passenger region sitting securely at the very center of the anomaly. This inner sanctuary is also perfectly flat. It is the protected pocket where the crew breathes, where the ship's hull remains solid, where mechanical clocks tick at their normal, comforting rhythm, and where the everyday laws of physics behave exactly as our terrestrial minds expect them to. Finally, there is the warping region, acting as the great mediator in between the two. This is the highly stressed shell of curved spacetime that performs all the unimaginable work, the boundary where the fabric of reality aggressively transitions from the flat interior to the flat exterior, creating the necessary compression ahead of the vessel and the corresponding expansion trailing behind it. By reducing the chaotic, wildly varied history of warp drive research down into this beautiful 3-region framework, the team at Applied Physics could finally begin to ask systematic, sweeping questions about the nature of space itself. They could look at their grand map and easily identify which territories of the design space had been heavily explored, and more importantly, which vast, uncharted territories had been completely ignored. What they discovered while gazing over this newly organized mathematical landscape was a profound reflection of human psychology. For almost 30 years, nearly every brilliant physicist who had touched this subject was singularly obsessed with one specific goal: going superluminal, traveling faster than the speed of light. It is entirely understandable. Breaking the ultimate speed limit of the universe was the entire romantic appeal of the concept, the grand promise whispered to us by generations of science fiction. If you are going to go through the staggering mathematical effort of bending the rules of space-time and risking a violation of causality, human ego dictates that you might as well go all the way and shatter the cosmic speed limit. But Bobrick and Martire pointed out a massive unlit corner of their new map that held a quieter, yet arguably more profound potential: the subluminal warp drive. These are theoretically designed space-time bubbles that manipulate reality in the exact same manner, but deliberately travel at constant velocities slower than the absolute speed of light. The scientific community had largely turned a blind eye to this concept because it lacked the theatrical magic of instantaneous galactic leaps. Yet, as the team meticulously calculated the constraints of these subluminal configurations, a beautiful reality began to emerge from the equations. Slower-than-light warp bubbles might actually be significantly easier to engineer, possessing the potential to perfectly satisfy the strict quantum energy conditions that the faster-than-light designs violently violated. They might not require the impossible, universe-breaking negative energy at all. And even though they bow in respect to Einstein's ultimate speed limit, their utility to human civilization would be nothing short of revolutionary. Imagine a spacecraft wrapped in a subluminal warp bubble, cruising smoothly at 90% of the speed of light. It does not break the sacred cosmic speed limit, but it fundamentally shrinks our neighborhood. It would effortlessly cross the vast, freezing expanse of our entire solar system in a matter of mere hours. It would reach the distant glow of Proxima Centauri in under 5 years of travel time. Most remarkably, it would achieve these blistering, unimaginable speeds while subjecting the fragile human crew inside to absolutely zero acceleration forces. Through this framework, the team also cemented a foundational theorem that elegantly brought the abstract mathematics back into the realm of conventional physics. They proved that any warp drive, regardless of how beautifully it is designed, acts effectively as a shell of matter that must be initially set into physical motion. A warp bubble does not simply snap into existence and teleport across the void. It is an object moving through space like any other, which means it still requires a conventional propulsion system to push it up to its cruising speed. The warp drive is not a magical replacement for rockets. It merely changes what the rocket is actually pushing. Instead of the engines violently accelerating the delicate human crew and the heavy cargo directly, the rocket only needs to accelerate the massive warp bubble itself. As the bubble accelerates through the dark, it gently carries everything resting inside its flat interior along for the ride, transmitting absolutely no crushing G-forces to the passengers. This realization completely reframed the 30-year-old puzzle. The warp drive was not a spell of wizardry, but a highly specific, structured geometry of space-time that, once physically pushed into motion, dragged a quiet room of flat space along with it. By classifying the abstract and accepting the speed limit, the researchers at Applied Physics quietly set the stage for a breakthrough that would finally untether human ambition from the realm of the impossible. The Applied Physics team had successfully mapped the abstract territories of the universe, classifying every conceivable shape a warp drive could take. They had organized the chaotic landscape of 30 years of theoretical physics into an elegant framework, But classifying a profound problem is entirely different from actually solving it. The ultimate question remains suspended in the quiet air of their Manhattan laboratory. Could a physical structure actually be designed within the newly illuminated subluminal territories of their map? The answer arrived in the spring of 2024, marking a moment that may one day be recorded as a quiet hinge in human history. On April 29th of that year, the journal Classical and Quantum Gravity published a paper bearing a highly technical but profoundly earth-shattering title: Constant Velocity Physical Warp Drive Solution. The lead author was Jared Fuchs, heavily supported by the entire collaborative brilliance of the applied physics team, including Christopher Helmerich, Alexei Bobrik, and Luke Sellers, all pulling together to focus their collective intellect on this single, seemingly insurmountable problem. What this specific paper claimed was nothing short of extraordinary within the rigid, unforgiving halls of theoretical physics. Fuchs and his colleagues presented a complete warp drive solution that flawlessly satisfied all of the classical energy conditions. To truly appreciate the gravity of this achievement, we must understand that the weak, null, dominant, and strong energy conditions are not arbitrary suggestions. They are the strict mathematical criteria that emerge directly from the bedrock of quantum field theory. They are the sacred rules that ordinary physical matter obeys, and that exotic matter violently violates. Violating these conditions almost always implies that you are dealing with a mathematical phantom, something fundamentally unphysical that the natural universe simply refuses to host. The Fuchs warp drive design violates absolutely none of them. It requires no negative energy anywhere in its vast geometric structure. It demands no exotic matter, and it relies on no violations of any physical principles ever observed in our universe. Instead, this groundbreaking design relies on an exquisite combination of two entirely physical elements. First, it requires a stable matter shell, possessing a very specific density distribution, constructed entirely from positive energy material. This is not the stuff of fantasy. This is ordinary baryonic matter. It is composed of the exact same protons, neutrons, and electrons that make up the screen you are looking at, the bed you are resting on, the earth beneath you, and the burning stars above. It requires absolutely no new, undiscovered physics to theoretically produce. Second, the design relies on a mathematical feature of the spacetime metric known as a shift vector distribution, which intricately describes how different regions of space are moving relative to one another. In this brilliant design, the shift vector creates a flowing pattern that perfectly mimics the compression and expansion of Miguel Alcubierre's original geometry. But crucially, this necessary compression and expansion are driven entirely by the distribution of ordinary mass in the shell, utilizing the natural, inward-pulling curvature of gravity itself interacting with the shift vector structure. Together, the physical shell of ordinary matter and the mathematical shift vector seamlessly produce a genuine warp effect, allowing a protected pocket of flat space to glide smoothly through the surrounding universe, carrying its cargo along for the silent ride. To rigorously test and validate this incredible design, the researchers utilized a highly specialized piece of diagnostic software they had developed and released publicly, aptly named Warp Factory. Written in the programming language MATLAB, this complex tool allows physicists to input any proposed warp metric and subject it to a grueling series of numerical calculations. It mercilessly interrogates the design, calculating the stress-energy tensor to reveal exactly what kind of matter would be needed, checking the energy conditions to see if that matter is physically possible, and producing detailed visual maps of how strongly the space-time is bending. When a proposed metric requires impossible, exotic matter, the visual output of Warp Factory is stained with the color red, a glaring signal of physical violation. But when the team ran the Fuchs metric through the rigorous algorithms of Warp Factory, the resulting visualization was breathtakingly clean. The output showed a beautiful deep blue everywhere across the entire structure. Blue is the mathematical color of reality. It indicates positive energy density, the kind that perfectly matches the ordinary matter of our known world. Dark, elegant lines trace the momentum flux, mapping the internal structure of how pure energy flowed through the bubble. Nowhere in the entire visualization did a single pixel of red appear. The Fuchs warp drive is entirely blue, entirely physical, and entirely consistent with every known law of physics we currently possess. The profound catch, of course, is the caveat that the sensationalist headlines often chose to quietly bury. This magnificent, perfectly blue solution is explicitly and permanently subluminal. The bubble moves at a constant velocity, and that velocity is strictly capped at less than the speed of light. The Fuchs design does not offer the romantic fantasy of faster-than-light travel. It will not allow human beings to reach the distant glow of Proxima Centauri in a matter of days or weeks, nor does it shatter Einstein's ultimate cosmic speed limit. Jared Fuchs himself was incredibly careful to emphasize this limitation in his public statements, clarifying that their concept will not deliver the rapid interstellar transport popularized by decades of science fiction. But what it does deliver is the warp effect itself. It provides the astonishing ability to accelerate passengers through the void without subjecting their fragile human bodies to any crushing G-forces, utilizing only regular physical matter. While it may not instantly grant us the entire galaxy, we must gently consider how a subluminal warp drive fundamentally transforms our immediate cosmic neighborhood. Let us look at the planet Mars. With our current, primitive chemical rockets, a journey to the red planet is a slow, agonizingly careful ballet of orbital mechanics that takes roughly 6 to 9 months to complete, heavily dependent on the perfect alignment of the planets. Our spacecraft must coast silently for almost the entire journey, because firing an engine continuously would require an impossible amount of heavy fuel and would produce acceleration forces that would crush the human crew. Launch windows for this tedious journey open only once every 26 months. Trajectories must be fixed far in advance, and the ability to make course corrections is severely limited. It is a cumbersome, highly restrictive, and incredibly dangerous way to travel. A subluminal warp bubble elegantly changes every single one of these terrifying parameters. Because the space inside the bubble remains perfectly flat and undisturbed, the crew experiences absolutely zero acceleration. A subluminal warp ship could theoretically fire its conventional engines continuously, pushing the massive bubble to a significant fraction of light speed, coast briefly through the dark, and then decelerate just as violently upon approach. Even if the bubble itself is accelerating at a rate that would normally shatter human bones, the passengers resting inside feel absolutely nothing but peace. The entire trip to Mars could be completely redefined, measured not in agonizing months, but in mere days. or possibly even hours if the acceleration were pushed high enough. The crew would step onto the rust-colored dust of the Martian surface completely fresh, unaffected by the brutal physical toll of long-duration spaceflight. This beautiful logic elegantly expands to the furthest, darkest reaches of our solar system. Jupiter, which is currently a multi-year voyage for our uncrewed probes, suddenly becomes a routine matter of weeks. The magnificent rings of Saturn, the freezing blue storms of Neptune, and the icy, lonely bodies of the Kuiper Belt all suddenly fall within the reach of short-duration, crewed missions. Humanity could launch grand expeditions to study these distant, freezing worlds up close, without demanding that astronauts sacrifice entire decades of their limited lifespans to the dark, silent journey. By surrendering the dream of breaking the ultimate speed limit, the applied physics team proved that warped spacetimes are not inherently dependent on exotic magic. For the very first time since the mathematics was written down 30 years ago, a warp drive design exists that does not demand an ingredient that the universe simply refuses to provide. It was a monumental victory for patience, a testament to the power of human intellect to find a beautiful, winding path through the most rigid laws of nature. The temptation of speed is a deeply ingrained characteristic of human ambition, a restless desire that constantly urges us to push beyond whatever boundary is placed in front of us. While a subluminal warp drive offers a beautiful, mathematically sound method of traversing our solar system in complete peace, the alluring promise of the stars whispers a different, more dangerous demand. If we have the mathematical blueprints to bend the very fabric of reality, the human ego insists that we must push that geometry to its absolute breaking point. We want to cross the cosmic ocean faster than the speed of light. However, the universe is not a passive playground for our engineering ambitions. It is an ancient, rigorous system governed by unyielding laws. And when you attempt to violently violate the sacred rule of causality, the physics of reality retaliates with terrifying severity. The true reason that faster-than-light travel remains so elusive has absolutely everything to do with a catastrophic phenomenon that occurs at the very front edge of the warp bubble, the exact moment it crosses that ultimate light barrier. When a structured pocket of space-time is forced to move faster than light, it violently tears the local fabric of reality, creating a deadly mathematical feature known as an event horizon. To understand the grim nature of a horizon, we must look at the most destructive and mysterious objects in the cosmos: black holes. A black hole possesses an event horizon, which is fundamentally a one-way boundary in space-time. At this terrifying threshold, the immense gravity causes the fabric of space to fall inward toward the center at a velocity that exceeds the speed of light. Because space itself is rushing inward faster than light can propagate outward, anything that crosses that invisible boundary can never escape. It is not merely that they are being pulled by an overwhelming physical force. It is that the actual geometry of space has been so profoundly twisted that all possible future-directed paths point exclusively inward toward destruction. There is simply no physical direction you can turn that leads back out into the open universe. A superluminal warp bubble generates a very similar, equally inescapable boundary structure, right at its leading edge. Imagine a human pilot sitting comfortably in the center of the flat, protected space inside the bubble. As the ship accelerates past the speed of light, the front wall of that bubble is now moving outward into the unknown faster than the speed of light itself. Because of this, a profound causal disconnect immediately descends upon the vessel. If that pilot attempts to send a radio signal or any form of information from their seat toward the front edge of the bubble, that signal will never, ever arrive. The front edge of the bubble is constantly receding into the distance faster than the light speed radio wave can propagate through the flat space to catch up to it. The signal will simply chase the front wall forever in the dark, never closing the gap, and therefore never having any physical influence on what happens at the boundary. From a practical, navigational standpoint, this creates a completely catastrophic reality. The ship's interior is permanently cut off from its own leading edge. During this unimaginably fast voyage, the pilot cannot steer the vessel. They cannot adjust their course to avoid an obstacle, and they cannot transmit any information ahead of their current position. The massive bending bubble must be aimed with absolute, flawless precision before launch, because once it crosses that superluminal threshold, the crew loses all causal access to the region of space they are violently hurtling toward. Any microscopic error in the initial trajectory cannot be corrected mid-flight, meaning the ship simply plows forward blindly on whatever vector it was initially set to, completely unable to respond to changing conditions in the void. The nightmare of this causal isolation deepens when you consider how such a journey would end. Because the pilot cannot send a signal to the front wall, a superluminal warp bubble cannot be stopped from the inside. To decelerate the ship and return to normal space, the drive would need to change its own geometry, shifting the delicate distribution of matter and energy in the warping region to relax the curvature. But executing that command requires sending electronic signals from the ship's interior computers to the boundary. Since those signals cannot reach the leading edge, you are entirely locked in a speeding cage of your own design. The pilot sitting in the control seat is instantly stripped of all agency, reduced to a helpless passenger watching the universe blur past through windows that no longer obey the normal flow of cause and effect. The only theoretical way to stop the vessel would be to have massive, pre-positioned external infrastructure waiting at the destination, a system set up by an earlier, slower mission that could somehow collapse the fast bubble from the outside, or perhaps some kind of autonomous mechanical timer embedded directly into the bubble wall itself before launch, programmed to shut the engines down after a specific duration. Neither of these options offers any comfort to a crew hurtling blind through the dark abyss. Yet, the inability to steer or stop is merely a navigational hazard. The universe has a much more violent, immediate defense mechanism waiting at that horizon, one involving an inescapable flood of lethal energy. In 1974, the brilliant physicist Stephen Hawking published a theoretical result that deeply shocked the global physics community. He mathematically proved that black holes, contrary to decades of prior assumption, are not perfectly black. Before this revelation, physicists believed these objects were cold, silent voids that only absorbed matter and never emitted anything back into the universe. But Hawking demonstrated that the strange, bubbling rules of quantum mechanics fundamentally alter this picture. In the incredibly empty vacuum of space, microscopic virtual particle pairs are constantly popping into existence out of absolutely nothing. Normally, these phantom pairs exist for an unimaginably tiny fraction of a second, and then immediately collide and annihilate each other, disappearing back into the vacuum without leaving a trace. However, when this microscopic dance occurs directly on the edge of an event horizon, something profound happens. The extreme geometry of the boundary violently separates the pair. One particle falls past the horizon into the black hole, while the other particle escapes out into the open universe. That escaping particle is suddenly rendered real, carrying actual energy away from the void. From the perspective of an outside observer, it appears as though the black hole itself is glowing, emitting a faint radiation into the cold dark. This phenomenon is known as Hawking radiation. When we apply this exact same quantum physics to the horizon created by a superluminal warp bubble, the mathematical results are nothing short of apocalyptic. The bubble's leading edge acts as a horizon where causal structure drastically changes, and wherever nature draws a horizon, Hawking radiation must inevitably appear. Right at the front wall of the speeding starship, virtual particle pairs continuously pop into existence. One particle falls forward into the unknown region of space the bubble is rushing into, while the other particle falls backward, directly into the ship's flat interior. From the terrified crew's perspective, a constant blinding stream of quantum particles begins raining inward from the leading edge. The severity of this radiation is dictated by a cruel mathematical inverse relationship. The temperature of Hawking radiation depends entirely on the physical size of the horizon. Larger black holes, like those with the mass of our Sun, emit incredibly cool radiation, roughly 60 billionths of a degree above absolute zero, rendering them entirely harmless and impossible to detect against the background of space. But smaller horizons emit vastly hotter radiation. Warp bubbles, by their very design, are exceptionally small compared to astrophysical black holes. A superluminal bubble pushing a spacecraft at 10 times the speed of light would possess an effective horizon radius measured only in a few tens of feet. Theoretical calculations published by physicists reveal that the Hawking temperature of a horizon that's small would instantly skyrocket to thousands or even millions of degrees Kelvin. It would be vastly hotter than the boiling, violent surface of our own Sun. The fragile human crew resting inside the bubble would not just feel uncomfortably warm. They would be immediately bathed in a catastrophic flood of high-energy particles pouring inward from the front wall. A dense, inescapable storm of X-rays and gamma rays would flood the cabin. The sheer intensity of this radiation would be completely lethal within seconds, tearing through human tissue and destroying the molecular structure of the ship. There is absolutely no physical escape, and no advanced shielding could ever hope to protect them, because the deadly radiation is not coming from the stars outside. It is being generated inside the bubble itself, in the narrow space between the ship's hull and the front wall of spacetime. Attempting to place a heavy physical shield between the crew and the radiation source would require disrupting the precise geometry of the bubble itself, which would instantly cause the entire warp drive to collapse into nothingness. It is the universe's ultimate, unbreachable defense, a wall of blinding quantum fire that guarantees any entity foolish enough to break the speed of light is instantly incinerated by the very fabric of reality they attempted to conquer. The space between the stars is universally perceived as a perfect, absolute void, a pristine emptiness stretching out into an endless, quiet dark. However, this common perception is a profound illusion. Interstellar space is not truly empty. It is thinly populated, resembling a delicate, invisible mist rather than a true vacuum. It is filled with stray hydrogen atoms, averaging roughly one solitary atom for every cubic centimeter of space. There are incredibly rare helium atoms, occasional microscopic grains of ancient cosmic dust, stray electrons, wandering ions, and high-energy cosmic rays violently expelled from distant, dying supernovae. For a spacecraft moving at our current, conventional speeds, this incredibly sparse medium is entirely negligible. A craft like Voyager 1 has been drifting peacefully through this faint cosmic fog for 50 years without suffering any catastrophic issue. The solitary atoms simply brush against the cold metal hull, harmlessly parting like water around a slow-moving boat. But the physical rules of interaction undergo a terrifying transformation when a vehicle is wrapped in a warp bubble moving at hundreds or thousands of times the speed of light. At those impossible velocities, this unimaginably thin gas ceases to be a harmless mist and suddenly becomes an apocalyptic problem. The terrifying mechanics of this interaction were meticulously worked out in a paper published in 2012 by a team of physicists, Brendan McMonagle, Geraint Lewis, and Philip O'Byrne. This team posed a simple, chilling question. What exactly happens to the interstellar medium when a superluminal warp bubble violently plows through it? The mathematical answer they uncovered was profoundly alarming. As the warp bubble rushes forward through the dark, the stray hydrogen atoms and microscopic dust particles floating in its path do not simply pass cleanly through the bubble's geometry. Instead, they become caught. They are violently trapped within the incredibly stressed, warped geometry resting exactly at the leading edge of the anomaly. The intense compression of spacetime at the front wall acts as a merciless cosmic plow, accelerating these trapped, microscopic particles to absolutely enormous, unfathomable energies. As the starship continues its silent journey, it accumulates more and more of this material, gradually building up a massive, highly energized reservoir of matter that is forced to travel exactly in step with the bubble. The danger of this accumulation is governed entirely by the sheer, crushing scale of interstellar distances. The longer the voyage lasts, the more devastating the gathering storm becomes. A trip spanning several light years would effortlessly sweep up billions upon billions of these tiny particles. Because of the extreme nature of the warp geometry, every single one of those trapped atoms is endowed with an amount of energy directly proportional to the bubble's blistering velocity. The ship is no longer just a vessel of exploration. It is entirely, albeit accidentally, transforming into a weapon of mass destruction on a scale previously unimaginable to human engineering. The true horror of this invisible payload remains hidden for the entire duration of the journey, safely locked within the bending curvature of the space-time wall, utterly imperceptible to the crew resting quietly in the flat space within. The tragedy of this mechanism reaches its absolute culmination at the exact moment the journey comes to an end. When the bubble finally arrives at its distant destination and the pilot initiates the shutdown sequence, the intense curvature of spacetime instantly relaxes, flattening back into the normal shape of the universe. In that fleeting fraction of a second, the invisible cage holding the reservoir dissolves, and all of that accumulated, highly energized matter is suddenly released. The the trapped particles do not drift away peacefully. They blast violently outward from the ship's current position in a tightly focused, blinding beam. This apocalyptic beam travels relentlessly in the exact direction the ship had been heading, firing directly toward the intended destination. The total energy contained within this release, according to the grim calculations of McMonagall and his colleagues, could easily be equivalent to hundreds of thousands of solar masses worth of pure kinetic energy, all tightly concentrated into a terribly narrow cone of destruction. The destructive capability of this release defies human comprehension. Absolutely anything caught within the path of that cone would be instantly and violently annihilated. If a human starship arrived at a beautiful, habitable world orbiting Proxima Centauri, the crew would not experience a graceful, historic landing. The resulting beam of energy would effectively sterilize the entire star system. Any planets unfortunate enough to be resting in the beam's direct path would instantly have their protective atmospheres violently stripped away and blown into the dark. Their solid, ancient surfaces would be mercilessly scorched all the way down to the bedrock. If the accumulated beam was intense enough from a particularly long journey, entire terrestrial worlds could possibly be vaporized entirely, reduced to glowing clouds of elemental dust. The brutal irony of this mechanism is that the starship itself, and the fragile crew resting inside, would completely survive the event. They would remain perfectly safe inside their protective bubble, right up until the release, completely shielded from the catastrophic blast. But the civilization that sent them, driven by a pure desire for peaceful exploration and scientific discovery, would have inadvertently committed a devastating act of interstellar destruction. In the quiet, clinical language of theoretical physics, this catastrophic scenario is sometimes referred to as the warp drive genocide problem. It is not a fringe hypothesis or a paranoid science fiction trope. The underlying mathematics are incredibly straightforward and unforgiving. The deadly effect scales perfectly with the total distance traveled and the density of the particles encountered along the way. Even the extremely low, almost non-existent density of the interstellar medium, when aggressively accumulated over the vast span of light years, produces a result that is undeniably devastating. Theoretical researchers have desperately proposed various solutions to mitigate this apocalyptic flaw. Some suggestions involve highly complex modifications to the bubble's geometry, attempting a hydrodynamic shaping of the front wall that might elegantly guide the incoming matter around the sides of the bubble, theoretically deflecting the particles rather than trapping them. Other proposals suggest altering the fundamental mission architecture, requiring the ship to end its superluminal voyage incredibly far away from the intended destination, stopping safely in the deep, empty void of space, and allowing the deadly beam to disperse harmlessly into the dark, before the ship slowly approaches the target star under conventional chemical propulsion. However, both of these theoretical ideas add layers of immense complexity to an already seemingly impossible engineering challenge. They introduce entirely new, poorly understood potential failure modes to a machine that already flirts with the very edges of physical reality. For any future mission planners, the particle accumulation problem dictates a grim reality. Superluminal warp ships could never, under any circumstances, approach inhabited or valuable star systems directly. They would strictly require elaborate arrival protocols, extremely long, carefully plotted deceleration zones, and absolutely precise alignment to ensure the exit beam is aimed safely away from anything of value. It would require advanced warning to any civilizations potentially residing at the destination, assuming they even exist and possess the technology necessary to receive such dire messages. This apocalyptic revelation is yet another massive complication, stacked heavily on top of the impossible exotic matter requirement. The terrifying causal isolation of the horizon problem, and the lethal inward rain of Hawking radiation. When you place all of these staggering issues together, the original, beautiful concept of the Alcubierre warp drive begins to look significantly less like a sleek, peaceful starship designed for human exploration, and far more like a clumsy, completely uncontrollable weapon of mass destruction that merely happens to transport cargo. It suggests a profound philosophical reality. Perhaps the laws of nature are not simply boundaries to be broken, but vital quarantine protocols designed to protect the fragile architecture of the cosmos from those who wish to move too fast. When confronted with the terrifying, seemingly insurmountable dangers of a superluminal warp bubble, the blinding radiation, the total loss of control, and the apocalyptic release of energy upon arrival, we are forced to ask if there is a gentler path through the dark. If warping space around a moving ship essentially weaponizes the cosmos, is there a different theoretical approach to faster-than-light travel that entirely avoids these violent consequences? The mathematics of the universe gently offers an alternative, though it is one wrapped in its own profound impossibilities. Instead of bending space around a vessel and forcing it to race across the void, imagine taking the fabric of reality itself and cutting a quiet, stationary tunnel directly through the cosmic dark. This would be a true shortcut, a hidden path connecting two unimaginably distant points along a route far shorter than the surrounding universe ordinarily allows. In this scenario, the starship does not need to move fast at all. It merely glides at a slow, peaceful velocity into the tunnel, emerging light years away just moments later. This beautiful, elegant concept is known as a wormhole. Much like the warp drive, traversable wormholes naturally emerge from the complex, sprawling mathematics of Einstein's equations as entirely valid theoretical solutions. The foundational concept was first mathematically described by Albert Einstein and Nathan Rosen in the year 1935, born from their deep study of black hole interiors, an anomaly that became known to history as the Einstein-Rosen bridge. However, those early mathematical bridges were unstable and completely untraversable, destined to collapse before even a photon of light could pass through. The dream of walking through the fabric of space remained dormant until 1988, when theoretical physicist Kip Thorne at Caltech, alongside his brilliant collaborators Michael Morris and Ulvi Yurtsever, published a transformative paper, inspired in part by a profound question from the astronomer and author Carl Sagan, who was searching for a scientifically plausible method of interstellar travel for his novel Contact. Thorne's team demonstrated that traversable wormholes were mathematically possible, provided certain absolute conditions were met. To visualize this majestic concept as you drift towards sleep, you must picture the vast three-dimensional expanse of spacetime as a simple, flat, two-dimensional sheet of paper. Normally, to journey from one point on that paper to another, a ship must crawl agonizingly across the entire flat surface. A wormhole is the equivalent of folding that paper through a higher dimension so that the two distant points touch, and then gently poking a hole straight through both layers to create a permanent shortcut. The physical distance through the hole is vastly shorter than the distance across the flat surface. The journey through the connecting throat does not exceed light speed locally. A photon racing through the tunnel would still only move at its standard velocity of 186,000 miles per second. But an outside observer, watching the vast expanse of normal space, would see the ship vanish into one mouth of the wormhole and magically reappear from the other almost instantly, potentially arriving long before any light signal taking the normal route could ever hope to make the journey. Unlike a warp drive, there is no violent bubble racing across the universe, just a permanent, fixed structure of space-time with entry and exit points that do not move. Yet, this elegant architectural dream harbors a fatal flaw. Gravity is an inherently attractive force. It constantly and relentlessly pulls matter and energy inward. A wormhole throat, being a delicate hollow tunnel carved through the heavy fabric of space-time, naturally wants to pinch shut under this immense, attractive pressure. It is inherently, violently unstable. To keep this cosmic throat open long enough for a fragile human ship to pass through safely, you need something that aggressively pushes outward against the crushing weight of reality, a substance that creates a repulsive gravitational effect. Once again, the unforgiving mathematics demands the impossible: exotic matter, that exact same phantom substance with a negative energy density that Miguel Alcubierre's original warp drive required. Kip Thorne calculated that holding open a traversable wormhole large enough for a modest, mile-scale spacecraft would require a staggering amount of this exotic matter, an amount roughly comparable to the mass of a large planet, arranged in a flawless, highly precise geometric shell around the throat. The margin for error in this architecture is absolute zero. If the exotic matter distribution fluctuates for even a microscopic fraction of a second, the delicate balance is lost, and the throat begins to collapse. Once this collapse begins, it proceeds catastrophically, pinching the wormhole shut in a fraction of a heartbeat, instantly crushing the ship and its crew out of existence. We are seemingly trapped again by the universe's demand for a magical substance that it refuses to provide in bulk. But there is one quiet, profoundly strange corner of the physical world where negative energy has actually been confirmed to exist, whispering a tiny promise from the shadows of the quantum realm. In the year 1948, a Dutch physicist named Hendrik Casimir, working at the Philips Research Laboratory in the Netherlands, was deeply immersed in studying the quantum behavior of electromagnetic fields. He made a bizarre, seemingly illogical prediction about the absolute vacuum of space. According to the chaotic, bubbling rules of quantum field theory, empty space is never truly, perfectly empty. It is a restless, seething ocean where virtual particles constantly pop into existence from the void, exist for an infinitesimal fraction of a second, and then annihilate each other back into nothingness. These fluctuations happen everywhere, at all times, throughout the entire cosmos. Casimir predicted that if you take two uncharged, perfectly parallel metal plates and place them incredibly close together in a pure vacuum, they will mysteriously attract each other. This delicate attraction is not caused by gravity, which is far too weak at such tiny scales, nor is it caused by static electricity, since the plates are entirely neutral. It is caused by the invisible pressure of the quantum vacuum itself. The plates are placed so close together that they restrict the chaotic dance of the void. Certain electromagnetic wavelengths simply cannot fit into the microscopic gap between the metals. Because those specific modes are excluded from the space between the plates, but continue to bounce and exist in the vast space outside of them, a fundamental imbalance is created. There are more virtual photons pressing on the outer surfaces of the plates than on the inner surfaces, creating a gentle, inexorable push that forces the plates together. This phenomenon, known as the Casimir effect, sounds like pure science fiction, but it is an absolute reality. It was first successfully measured experimentally in 1997 by Steve Lamoureux at the Los Alamos National Laboratory, using plates separated by gaps of about 1 micrometer, roughly 1,000th of a single millimeter. What matters most deeply for the dream of interstellar travel is the profound, earth-shattering implication of this tiny, invisible force. The trapped region between those Casimir plates genuinely possesses a lower energy density than the normal empty vacuum outside. It is lower than ordinary empty space, which means, by definition, it possesses a true negative energy density relative to the cosmic baseline. It is the only confirmed example in all of physics where genuine, measurable, persistent negative energy actually exists, proving definitively that nature does not completely forbid its presence. But the scale of this quantum miracle offers a heartbreaking reality check for any hopeful mission planner. The amount of negative energy produced inside a Casimir cavity is unbelievably, agonizingly tiny. A pair of plates measuring 1 square meter in area, separated by that tiny 1 micrometer gap, produces a total negative energy on the order of 10 to the negative 7th joules, which is 1/10,000,000th of a single joule. To put that minuscule whisper of energy into a human perspective, it is less energy than it takes a single mosquito to flap its delicate wings just 1 time. Meanwhile, a traversable wormhole or a superluminal warp drive demands negative energy measured in kilograms or tons of mass equivalent. Utilizing Einstein's famous equation, where energy equals mass times the speed of light squared, just 1 single kilogram of mass corresponds to roughly 9 times 10 to the 17th joules of energy. The crushing gap between the microscopic energy a Casimir cavity provides and the staggering power the mathematics of the cosmos demands is roughly 24 orders of magnitude. That is a difference of a trillion times. The exotic matter is real, quietly proving its existence in the darkest, smallest corners of the laboratory. But scaling a mosquito's single heartbeat up to the overwhelming weight of an entire planet remains an engineering chasm that humanity may never possess the strength to cross. But what if, somewhere in the vast, silent dark of the cosmos, another ancient civilization has already solved this impossible puzzle? If warp drives exist anywhere in the universe, and if they occasionally suffer from catastrophic failure, we might actually possess a way to detect their ghostly echoes washing over our world. In the year 2024, a theoretical physicist named Katie Clough, alongside her collaborators at Queen Mary University of London, published a deeply fascinating paper in the esteemed journal Classical and Quantum Gravity. The paper carried a beautifully poetic title, What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse. This team posed a profound, haunting question that no one in the scientific community had ever seriously addressed before. What exact observable signature would the universe produce when a warp bubble catastrophically fails? A warp bubble is not a solid object. It is an incredibly stressed, highly structured region of spacetime held together by a flawless, delicate distribution of matter and energy. If that delicate distribution becomes unstable for even a fraction of a microscopic second, the bubble does not merely fade away into the night. It collapses rapidly, violently, and catastrophically. The heavily curved space-time geometry suddenly and aggressively relaxes back to its flat, natural state, and all of the immense energy that was artificially stored in that curvature gets released instantly into the void. Clough's team utilized the immense power of numerical relativity simulations to meticulously model this catastrophic event. This is the exact same complex branch of computational physics, running on massive supercomputers, that scientists currently use to simulate the cataclysmic mergers of black holes and the violent collisions of neutron stars, the very events that our earthly observatories regularly detect. They constructed a mathematical warp bubble within their supercomputer, gave it a physically reasonable matter distribution, intentionally introduced a tiny, fatal instability, and then let the simulation run to its violent conclusion. As the theoretical bubble collapsed in the simulation, it emitted powerful gravitational waves, which are literal, physical ripples in the fabric of space-time itself, propagating outward in all directions at the exact speed of light. The resulting waveform possessed a highly specific, unique shape. A brief, violent burst of high-frequency oscillations, followed immediately by a decaying ring-down pattern as the geometry of space finally settled back into peace. This overall signature was entirely distinct from any known astrophysical source in the universe, fundamentally different from the familiar chirping signals of merging black holes or the chaotic noise of exploding supernovae. For a failing warp bubble with a physical diameter of a few miles, the team calculated that the dominant frequency of these space-time ripples would reside around 300 kilohertz, or 300,000 cycles per second. This specific, incredibly high frequency creates both a fascinating problem and a beautiful, unprecedented opportunity for humanity. Our current, massive gravitational wave observatories, such as LIGO, are specifically designed to listen to the deep, low-frequency bass notes of the universe, operating strictly in the range of 10 Hz to a few kilohertz. A warp drive collapse, screaming out across the void at 300 kilohertz, is completely outside of LIGO's detection band. Even if one collapsed in our own Milky Way galaxy, our current ears would be entirely deaf to it. But future, high-frequency gravitational wave observatories, currently in the conceptual stages of development, could one day open a completely new window on the gravitational sky. Instruments utilizing superconducting resonators or levitated sensors could theoretically tune into this exact frequency. This realization completely shifts the paradigm of our ongoing search for extraterrestrial intelligence. For decades, humanity has pointed massive radio telescopes at the stars, anxiously scanning the sky for artificial electromagnetic transmissions, laser pulses, or the waste heat of massive structures, constantly assuming that advanced aliens communicate or leak radiation exactly as we do. But if a truly advanced civilization operates warp drives to cross the stars, and if those drives occasionally fail in the unforgiving dark, the resulting gravitational waves would propagate outward forever, eventually washing over our tiny blue planet like a silent tide. By purposefully searching for these specific waveforms, we are no longer just looking for intentional messages. We are quietly listening for the distant, tragic echoes of their advanced engineering. It offers a tantalizing possibility that even if we never build a starship ourselves, we might one day feel the gravitational footsteps of those who did. This brings us to the final, quiet truth of our long journey tonight. When we ask the ultimate question of whether humanity has finally found a real way to travel faster than light, the answer requires a deep, honest reflection on the subtle boundary between pure fantasy and extreme engineering. What the mathematics explicitly says yes to is profoundly significant. Warp drive as a solution to Einstein's field equations is completely valid, and it has remained valid ever since Miguel Alcubierre first proved it in 1994. Furthermore, the breathtaking work of the applied physics team in 2024 proved that warp drives do not necessarily require impossible, physics-breaking exotic matter, at least not for designs that stay strictly below the speed of light. They provided humanity with a genuine, physically sound mathematical solution, utilizing only ordinary, positive energy matter. This moves the concept entirely out of the realm of magic and into the realm of plausible, albeit distant, engineering. But the mathematics still firmly and relentlessly says no to faster-than-light travel without that magical negative energy. The ultimate cosmic speed limit remains an absolute, terrifying barrier, guarding the secrets of the distant stars just as fiercely as it always has. The interstellar voyages of popular science fiction, where sleek starships casually hop between star systems in a matter of days and crews visit dozens of alien worlds in a single career, remain firmly rooted in fantasy. But fantasy is not the same thing as impossibility, and that distinction is everything. A fantasy violates the fundamental laws of nature, requiring magic or a complete suspension of disbelief to exist. A long-term engineering goal, however, is entirely consistent with known physics, no matter how ridiculously difficult, incomprehensibly expensive, or centuries away it might actually be. The subluminal warp drive clearly and undeniably clears that bar. It clears it with countless caveats, with terrifying energy requirements, and with material science that we will not possess for centuries, but it does clear it. The theoretical research community continues to build upon that quiet foundation, writing new papers, running new simulations, and expanding the solution space slowly, one agonizing equation at a time. We are currently a civilization that takes immense, justified pride in having walked on the desolate dust of our moon, successfully landed robotic rovers on the rusty plains of Mars, detected the invisible ripples of black holes colliding billions of light years away, and photographed the shadow of a supermassive black hole at the center of a distant galaxy. A species with that level of relentless, stubborn curiosity does not simply give up on a problem just because the numbers look unimaginably hard. Humanity may never actually leave the solar system with a warp drive. Our fragile civilization might collapse long before we ever develop the technology, or we might eventually discover a deeper, hidden law of physics that forbids it after all. But the alternative is equally possible. In some distant century, a dedicated research team might crack the final problems, build the very first test bubble, and eventually, humanity might light up a warp drive for the first time, crossing the terrifying 25 trillion miles to Proxima Centauri, not in 70,000 years, but in just a few short years. The engineering is centuries away, but the equations are written. The simulations are quietly running in the dark, and the distant dream is now firmly anchored in reality. As you close your eyes and let the silence of the night take over your room, remember that the distance to the stars is vast, but human patience is infinite. Somewhere in a future we cannot quite see yet, the very first human warp bubble might be learning exactly how to bend space itself. Rest now, let go of the heavy earthly anchors, and know that the universe is full of mysteries waiting patiently to be solved. Good night and sleep well from Bedtime Universe.